Alright, so in this video, we're going to be talking about circular motion. We're going to be talking about the difference between linear speed and angular speed. And what I want to do is, along with this video, I have posted a separate video of a link to someone who kind of explains the difference between linear and angular speed, and I think it was a really good video, so I attached it to this presentation as video number 2, so that if you are having any confusion or just not quite sure what I'm talking about, she does a nice little visual representation of it, so I thought that would help. So we're going to be looking at these two different speeds, or velocities as you want to think too, and then also I'm going to be showing you how to use some dimensional analysis, also known as unit conversions, to be able to solve some of these scenarios too. So let's go ahead and talk about the two different types of velocities. We have the linear speed as well as the angular speed. So arc length is going to be used to analyze our circular motion, which we talked about yesterday. So the rate at which an object moves along a path is called its linear speed. Okay, so which kind of makes sense. It means you're moving a car, that's its linear speed. And then there is what's called the angular speed, which is the rate at which the central angle changes along the path is called. So in the video that I'm going to attach this, she does a really nice job explaining the difference between these two. Now the math side of things, taking a look at the linear speed formula, which we're going to represent as V, what we're going to do is we're going to take our arc length of S and we are going to divide it by time. So we're going to take the arc length of our circle that we're looking at and divide that by the amount of time. Think about right here, miles per hour. When you are driving a car and you are moving the car, you are going a certain number of miles per hour. You're looking at the arc length being how many miles is that wheel turning, and then over a given amount of time. So right there, you're looking at your linear speed. Angular speed here, we're going to be using a W to note that. This time you're going to be taking the central angle, which is that angle of theta that we've been talking about, and we're going to divide that by time. And so we're going to take our central angle and divide that by the amount of time. So just a reminder to you that with arc length, I'm going to be using the formula of theta times r. And so we are going to be having theta in radians, which, using this whole idea of radians, is going to make things a little bit easier, especially once we get to the dimensional analysis part. So we're going to take a look at an example here and look at how do we find the linear speed as well as the angular speed. So a bicycle tire of 14 inches rotates at a rate of 125 revolutions per minute. And so we're going to note that as RPM. And one revolution is just one time around a circle. So thinking about here that in 1 minute, that tire is going to be spinning 125 times. And we've got the length, or the diameter, what is it? We've got the bicycle tire of 14 inches. So, and that is supposed to, this 14 inches is going to be our, I'm going to just double check, that is going to be our radius. So when we talk about that, yeah, it's supposed to have a radius of 14 inches. I just forgot to write that in. So, to find the linear speed, what we need to do here is we have to find the arc length and divide that by the amount of time that we're looking for. And here we're trying to find the linear speed of the tire in inches per minute is what we're looking to do. So going ahead and trying to find out what our arc length is going to be. Now if it says that it makes 125 revolutions in 1 minute, that means that we are making, I'm going to take theta times r. So our value of theta that we're looking for, it's making 125 of these full revolutions. So our value of theta is 2 pi. our radius, which is 14 inches. And now the fact that you are making 125 of those revolutions, that means we need to take that arc length of 18 pi and multiply it by 125. So our arc length that we are now going to get here is 3,500 pi, and that would be in inches. And so that right there is your arc length. And now to find our velocity, to find our linear speed here, we're going to take our arc length, which is 3,500 pi, and I'm going to divide it by the time, which is 1 minute. Oops. And so now what we have here is we have the linear speed in inches per minute. And if I want to go ahead, I can simplify this or approximate it to being 10,995.6 inches per minute. Seems like a large number, but you are also measuring in inches and not like miles. Looking at the angular speed, so this time we are going to be taking our value of theta, dividing it by the amount of time. So it says find the angular speed of the tire in rotations per minute. So when we take a look at the central angle, that right there is, we're going to again use radians. So we are going to be saying that theta here is equal to 2 pi. But we've got to understand that, we are doing 125 revolutions. So if you think about it, you're taking 360 degrees and multiplying that by 125. So we're going to take 2 pi radians and multiply that by 125. And so that ends up giving us 250 pi radians as far as our angle. So then to find our angular speed, we're going to take that 250 pi radians and divide it by 1 minute. And so what we now have is we have the number of radians per minute. If I simplify this down, I get 785.4 radians per minute. I'm going to go ahead and do another example. One thing that I'm going to suggest too with this video is that at any point you might want to go back and just watch an example being done again. Even after maybe you've taken some notes, pause it, go back and re-watch it again just to kind of help you. If you get stuck on the assignment, also you can get back onto the video and watch an example being done once again for you. That's the beauty of having all of this. All right, so here we have a DVD with a diameter of 120 millimeters, rotates at a rate of 45 revolutions per minute. Find the linear speed of the DVD in inches per minute. So starting out, we got to find our arc length. So we're going to take theta times r. We need to know our radius, which here it's telling me that we have a diameter of 120. So that tells us that our radius is going to be 60 millimeters. So then our arc length here, we are making full revolutions. We're making 45 of them to be exact. So our value of theta is going to be 2 pi times 60, which is 1 rotation. And then we are going to go ahead and multiply that by 45. And this is going to end up giving me 5,400 pi. And that would be measured in millimeters. And so then to find our linear speed, I'm going to take that 5,400 pi and divide it by 1 minute. Millimeters. And if I now approximate this here, I'm going to get about 16,946.6, and that's going to be millimeters per minute. Again, it's a very large number, but we are measuring in millimeters. If we had something like measuring in feet, it's going to be much less. All right, let's do one more example, then finding the angular speed. So here we are looking at figuring out what our value of theta is. So since we're making, again, 45 full revolutions, 1 revolution is 2 pi radians. So if we multiply that by 45, That takes us to 90 pi radians. As far as how many total radians we are working with, again, if you think about this in degrees, you're taking 360 degrees and multiplying that by 45. And that's how many total degrees. We're just using the radian measure. So then to find our angular speed, we're going to take that value of theta. So we're going to take 90 pi. We're going to take that number of radians and we're going to divide it by 1 minute since we're working with rotations per minute. And then if we go ahead and take 90 pi divided by 1, we're going to get 282.7, and that would be radians per minute. So hopefully those two examples make sense and are able to help you find linear speed as well as angular speed. What I'd like to do next is do an example, kind of the same thing, along with dealing with some unit conversions. So it says we have a windmill that has blades that are 14 feet long. If the windmill is rotating at 5 revolutions per second, find the linear speed of the tips of the blades in miles per hour. So a couple things here. First of all, keywords. It's asking us to find the linear speed. So that tells me that I'm going to be working with S is equal to theta times R. I'm sorry. Thank you. I want to find the speed. So I'm looking at V is equal to S over T. Sorry about that. And in order to do so here, that means that we have to figure out what our arc length is. Then the other thing that I want you to look at here is notice that it wants you to find the linear speed in miles per hour. And eventually, when we look at the beginning here, everything that's being given to us here is in 5 revolutions per second. So we're going to have some things that we're going to have to convert. So starting out with knowing that we have to find our arc length, I need to take my value of theta times R. And theta, we're working with 5 full revolutions. We have a windmill that the blades are 14 feet long, so that right there is going to be your radius. So if we take 2 pi and we multiply that by 14, that would give us the arc length of 1 full circle. We are looking at 5 of those full circles, so I need to multiply that out even further. So this is going to give us 140 pi total feet that the windmill is covering. So now to go ahead and to find our velocity here, we're going to take 140 pi feet. And since you are working with eventually your 5 revolutions per second, that means that we need to be taking the 140 pi divided by 1 second. So if I was, I mean, that kind of makes sense of where we would be at for our linear speed if we are looking for feet per second. But now we have to make the conversions into miles per hour, so we're going to start using some unit conversions. If you have...
How about some nachos? Want some nachos?
I'm okay, dear. So now you have to, if you've had chemistry, now I can't keep a straight face after my husband just did that. All right, so now if you have taken chemistry, you've probably done unit conversions, so that might be something, or something that's not so new, or maybe this might be brand new to you, and I will try and walk you through it. So we're trying to convert from feet per second, and we want to convert it to miles per hour. So you got to think of which one you want to convert first. Do you want to convert the feet to miles, or do you want to go the seconds to hours? I'm going to go ahead and start with the seconds. I know that there are, and we're going to take one step at a time here. Some of you guys would be able to take some larger leaps. I'm just going to start real basic. And the fact that I know that in 1 minute, there's 30 seconds. So what's going to happen here is I'm going to set up another fraction, or I'm sorry, not 30 seconds, 60 seconds. So there are 60 seconds in 1 minute. And with how I'm setting this up here, because I'm taking 140 pi feet over 1 second, thinking about how variables cancel out, when we divide something here, your seconds are going to be canceling each other out. And so what this would then leave us with is we'd take 140 pi times 60 all over 1, because 1 times 1, and now I would have converted this into feet per minute. So that's kind of the whole idea behind this. So I'm going to rewrite this a little nicer here for a second. All right, so multiplying this by 60 seconds is equal to 1 minute. I'm going to be able to cancel out the seconds. Okay, so now I'm at feet per minute. All right, now I need to get from minutes into hours. So since minute is down here in the denominator, I need to put the minutes up here in the numerator so that they would cancel each other out. So I know that there are 60 minutes in 1 hour. And so now here we are canceling things out, and you've gone from having something in feet per seconds to now you have feet per hour. So we are very close to being done with this. Now we just have to transfer it into having, instead of feet, we have to convert it into miles. Some of you, hopefully you might know how many feet are actually in a mile. There's 5,280 feet in 1 mile. So since I have the feet up in the numerator, I need to put the feet down here in the denominator. And I can say that there are 5,280 feet in 1 mile. And so lastly here, my feet is going to cancel out. And so if I look at all my units here, they've all canceled out except for miles per hour. So now we just go ahead and we take our calculator, and we're going to take 140 pi times 60 times 60 times 1, and then we'll divide that by 1 times 1 times 1 times 5,280. And so you put that into your calculator and you end up with 299.9 miles per hour. Okay, I'm going to show you another example of using the unit conversions here. When you are given a idea of a ceiling fan where we have a certain radius and then you're given some rotations per minute, and we want to find the linear speed of the blades. So, and we're going to change it into feet per second. Okay, so that's our goal. So right now, the fact that we have this idea, we have this fan that rotates 40 RPM. So that means revolutions per minute, or rotations per minute. So if I start this out here, I am looking at using 40 rotations or revolutions. I'm going to use the word revolutions here. So 40 revolutions for 1 minute. And to answer the question then, to find the linear speed of feet per second, we're just going to use some unit conversions. So using the idea of, I'm going to start with the time, so go from minutes to seconds. And I know that there are 60 seconds in 1 minute. So since minute is down here in my denominator, I'm going to go ahead and put minutes up here in my numerator. And I know that there are, in 1 minute, there are 60 seconds. So I can start this out, that create a little proportion here, and then our minutes, oops, sorry, I didn't need to put an equal sign here. This should be just a multiplication sign. So the minutes are going to cancel out. So now if I cancel, when I move this across here, I would get 40 over 60 revolutions per second. So I've got the second part. Now I just need to end up converting the revolutions into feet. So here's where it gets a little bit tricky, starting to get this whole idea of what a revolution is. Well, a revolution is one time around a circle. So if I think about this here, I need to somehow convert it from revolutions into feet. How I can do that is by involving our arc length. So if I have revolutions up here in the numerator, I'm going to go ahead and put revolutions down here in the denominator. And in one revolution, my circle is going to rotate 2 pi radians. Okay, one revolution is equal to 2 pi radians. So now what I've done here is I've canceled out the revolutions, and now we are sitting here looking at having it be in radians. So now how are we going to cancel this out and get from radians into feet? Well, here's the idea of what a radian is. Remember that 1 radian is equal to the radius of your circle. So if I know that my ceiling fan has a 25-inch blade, that means that the radius is going to be 25 inches. So then here, if I look at the number of radians, so radians here, 1 radian is equal to the 1 radian is going to be equal to my radius. And so since my radius is 25 inches, so 25 inches is equal to 1 radian. So now I'm able to cancel out my radians, and I am currently in inches per second. And now we just need to convert this from inches into feet. And since there are 12 inches in 1 foot, inches is in my numerator here, I'm going to put it in my denominator. And I have 12 inches is equivalent to 1 foot. And so now our inches are going to cancel each other out. And we can go ahead and we can multiply this all out. So I'm going to take 40 times 1 times 2 pi times 25 times 1. Which I'm going to grab my calculator real quick. Alright, so once I multiplied this all out, then I ended up getting 2,000 pi, and that would be feet over 720 seconds. And so then that was going to simplify down to 8.727, and we would end up with feet per second. So here we've gone through definitely a little bit more of some challenging stuff to look at, especially with the unit conversions. But again, watch the videos if you need to a couple times, and work with each other, help each other out. And if you have any questions, try and write them down so we can go over them on Monday.